All right. So to start off, a couple of announcements. First announcement is final project dataset due this Saturday. Any questions on that assignment? Yeah. I mean, probably like sort through it to some extent. Like the objective is to make sure that you have a data set that you know will work for your problem and a way to interface with it. So not necessarily. I mean, it depends on how much work that's going to be. We're trying to give you a checkpoint that sets you up for success and helps you to catch any potential failure modes due to your data set as early as possible. So I don't know if that helps. Yeah, question. A PyTorch interface to the data set. Yeah, I've gotten a lot of questions on that. So I updated the requirements on Learning Suite to be a bit more specific. But what we're looking for is something that, like a dataset class, a PyTorch dataset class that inherits from torch.utils.data.dataset. So like you've had in your previous labs, just a PyTorch dataset that shows you can load your dataset into something like that PyTorch can work with and that you can train a neural network on. Okay, anything else? Yeah, Grant. Oh, and you're talking about for your specific project? Gotcha. So I mean, I would say, yeah, if the specific data set specs don't apply perfectly to your project, turn something in that is relevant to your project. Yeah, this assignment was made for you. You were not made for this assignment, as Jesus would say. Okay, so all right, so that's final project dataset due this Saturday. Deep reinforcement lab. Ben has been, who's our main TA, who has the most hours, has been out of town this week. And so we haven't had a lot of TA availability to help. And so this lab is getting pushed to next Saturday. Everyone, any objections to that? All right, good. Okay, so yeah, and actually, Matthew, can I ask you to post on Slack about that just so people are all aware? That'd be great. Yeah. The project that was going to be due next Saturday will be due the following Saturday. Yep. Yep. Okay. So this is gonna be our last look at the policy gradient algorithm. I want to give you one more shot to yeah, try to understand this and ask questions if you still don't. So yeah, take a couple minutes, turn to your neighbor and see if you can explain this statement in blue. If advantage is positive, gradient of loss is positive, and we increase likelihood of action in the future. And if the advantage is negative, the likelihood is decreased. Oh, and actually, let me just emphasize this as well before you try to do that. This pi of ATST, as well as the advantage, these are each calculated for a single action. So these are not vectors. So pi of STA is a vector, but then we take a specific action out of that vector based on the action that was actually taken during the rollout. And same deal with getting the advantage. The advantage is the advantage based on the action that was the rewards that were actually received during your rollout. Yeah, so these are both scalars. And yeah, see if you can explain this statement to your neighbor. Okay. Anyone feeling like they're still having a hard time explaining this? All right, Haley, do you want to take a shot at explaining it and see how? Yeah. Okay, A hat. Correct. Yeah, and you said it was the error. Usually our errors are going to be like they're going to be like distances. So this is a little bit different from an error just because it's signed. So it's either positive, it can be either positive or negative. And that's really important when telling like this whole policy gradient loss depends on the sign of that advantage. Yeah, so you're totally right. So the pi sub theta of AT-ST is the probability that the network said that we would take action T out of state T. Yeah, so the E hat is the expectation across time steps. So we're going to average over, we could average over a rollout. In this case, we're just going to sample, we're going to have multiple rollouts, and we're going to basically sample random time steps from random rollouts. Mm-hmm. Yeah. Yeah, the rollout's going to be start to end or any interval. Mm-hmm. Yeah, Joseph. Why do we have the gamma? Yeah, so the gamma is the discounted, is the discount factor for future rewards. And it basically says we want to prioritize rewards in the near present as opposed to rewards in the distant future. Yeah. Well, so positive, I wouldn't say it's a good thing. Like in the end, we want our advantage function to be 0, or our advantage to be 0, because it means that our value network is perfectly predicting the reward that we will get. And so an advantage being positive just tells us that we want to increase the probability of that action according to our network. Because basically it means that a positive advantage means that our network probability of that action is not high enough considering the value that we're getting out of it. Yeah. Good question. So the log is just the log of the policy, not of the advantage. Yeah. So it's just the log of this the probability of that action. Mm-hmm. Yeah, Craig. We are learning the value function. Yep. So V of ST is a parameterized neural network. Yes, we have a network for the policy and for the value function. Mm-hmm. And the policy we're calling our actor, and the value function we're calling our critic. Those are just kind of like colloquial terms to refer to these policy and value networks. Sam. You said typically the gradient's like a vector. Good question. So yeah, there's kind of some nuance here. So the gradient of this function with respect to the action taken will be positive, but the gradient with respect to the network weights might be positive or negative, whatever you need it to be to make the probability of the action go up. Does that make sense? So there's a, and yeah, so the gradient with respect to the given action is just a derivative, and it can be positive or negative, but then when you do the chain rule of derivatives to the parameters, then it becomes a gradient. Okay. All right. So we have more GANs today. So as a review, here's our setup. We have a discriminator neural network, which is here on the top left and the top right. And we have a generator network, which is here on the bottom right. And we want our discriminator network to learn to distinguish between real images from our data set and generated images from the generator. And we want the generator to learn to produce images that fool the discriminator into thinking that they are realistic. And so to do that, we will sample a vector z from a high-dimensional Gaussian distribution, feed that into our generator, and generate a sample that corresponds to the z vector sampled from our high-dimensional Gaussian distribution. So how do we train this? This is the what we call our minimax objective function for training GANs. Let's see if we can break this down. So we want to minimize over G and maximize over D this function. So the discriminator wants to maximize this, or maximize the value of this function, and the generator wants to minimize the value of this function. So yeah, and so D of X will be a probability between 0 and 1, with 0 being fake and 1 being real. And so with that in mind, the fact that D of X is 0 if fake and 1 if real, think about how, whether you agree that the discriminator see if you can convince yourself that the discriminator wants to maximize this function. So let's walk through this. So if we plug in if we have D of X, and also, so X is sampled from the true data distribution, and Z is our sampled Z vector. So on the left-hand side, we have our real images, and on the right-hand side, we have our fake images. So if the discriminator is trying to maximize the left side of this equation, how will that work? Well, if D of X equals 1, then log of D of X equals 0. Versus if D of X is 0, what will log of dx be? Negative infinity. And so, yeah. So are we in agreement that we want that the left side of this equation will be maximized when the discriminator perfectly classifies real images? Yeah, Max. Not really, because in reality, the discriminator will never predict exactly 0. We're just trying to show kind of like the range of values that this can take. Yeah, Matthew. Tilde means, good question. That means sampled from. So so for this left side, we have X sampled from our true data distribution, just X taken out of our data set. And in the right-hand side, we have Z sampled from a high-dimensional Gaussian distribution. All right, so let's do the right side of this equation for the discriminator. So what do we want the discriminator to output for fake images? Yeah, we want, well, so for the fake images, we want the discriminator to output 0, right? Exactly. Or what? Wait, let's see. So d of 0, which is what we want it to be, is 0. The log, this becomes log of 1 minus 0 is log of 1, which is 0. And yeah, versus if we put 1 here, then yeah, if the discriminator outputs 1, then we'll have 1 minus 1. Log of that is negative infinity. And so yeah, this right side will be maximized when D predicts 1 or predicts 0 for fake images. Think about that for a second. Yeah, so this log of 1 minus d of g will have the value 0 when D predicts 0, and negative infinity when D predicts 1. Yeah, Sam. Correct, yeah. D spitting out 0 means that it thinks the image is fake, and 1 means that it thinks the image is real. Okay, are we pretty convinced that this is the right objective for our discriminator? Yeah, Brendan. Good question. So why do we have the min G max D? We've only talked about the discriminator. So if we were just trying to train a perfect discriminator, all we would need is the max over D. So yeah, now let's talk about the min over G. So how is this first term affected by G? Not at all, right? There's no G in there. How about the second term? How can G maximize? Let's assume our discriminator is frozen. How can G maximize the right side of this equation? First question is, what is the type of output of G of Z? What kind? It's an image, right? So G of Z is an image. And so how can we minimize the right side of this equation with an image predicted by G? We want to make D think that it is 1, right? We want the discriminator to think it's real. And so let's run this through. So let's say that we fail to fool the discriminator. The discriminator thinks our generated image is fake. It figured us out. In this case, the right side, then D of G of Z would be 0. The log of 1 minus 0 would be 0. And yeah, versus if we fool the discriminator, we'll hit D of G of Z will be 1. So we have log of 0 is negative infinity. And remember, we're trying to minimize the right side of this equation. And so this right side of the equation will be minimized when G fools the discriminator into predicting that the image is real, into predicting D of G of Z is 1. The generator wants to make D of G of Z 1, basically. Okay, so do you see how these are kind of competing objectives? How the discriminator is trying to make this right-hand term go up, and the generator is trying to make the right-hand term go down? Okay. And then, yeah, just a practical matter. So And this kind of relates to the question on numerics about dealing with negative infinities. So in practice, to estimate G, we maximize log of D of G of Z and just leave out the 1. And that gives us, this basically gives us stronger gradients for G when the discriminator is very strong. Okay, so then we don't need to worry too much about this. This is just a theorem that shows that given a perfect model, the discriminator should predict that should predict a value equal to the probability that the data came from the true distribution over the probability that the data came from the true distribution plus the probability that it came from the fake distribution. And so this is a snapshot of what this might look like when we're trading off optimizing D and G. So here on the left-hand side, we have a model with basically an initialized model. So we have the data distribution is in these the black dots. The generator distribution is given by the green solid line, and the discriminator has to learn some decision boundary between these two distributions. And so we're going to update D and basically to try to discriminate between samples from the true data distribution and from the generated distribution. And this blue dashed line that looks kind of sigmoidish, this is following that formula from the previous slide where it's saying that the probability that D of X is probability of data over probability of data plus probability of model. So that's how we get this blue line. And you can see that it's probably going to be able to discriminate pretty well between the between the samples under the dotted distribution and the samples under the solid distribution. Any questions for this first step of updating the discriminator? Okay, so we've updated our discriminator. Now we want to update our generator to fool our discriminator. So the generator looks at this decision boundary and says, oh, if I can push my samples more in the direction of the true distribution, I can fool this discriminator more often. And so you can see that the generated distribution starts to approach the data distribution. And eventually, after they've traded off for a while, the final equilibrium hopefully will look something like this, where our generated distribution matches the data distribution perfectly, and this discriminator is unable to distinguish between the two. We're going to take a look at a demo of how that works. So this is a GAN fitting just a simple Gaussian distribution. So the dashed blue lines are the data distribution. The red line is the discriminator probability and probability of being real. And the green distribution is our generative model, which is learning to produce samples that match the data distribution. And to be honest, does anything about this look weird to any of you? Yeah, that's what I'm noticing as well. So Chase pointed out that the discriminator is classifying things off of the distribution for both of these with a value of 1. Any ideas why that might be? Yeah, that's my guess, is that the generator that there really aren't any samples outside this range in the training data set. And so there's no real penalty for the discriminator predicting 1 for anything outside that range. So I wouldn't worry a ton about that. Although you can imagine if you try to optimize off of this surface, then you could run into issues with your discriminator no longer being reliable, which is kind of interesting. Okay, so that is our toy example. Okay. So this is the full GAN training algorithm. So first we sample a batch of noise samples of Z vectors from that high dimensional Gaussian distribution. Then we sample a mini batch of data examples, x1 to xm. And we will start by updating the discriminator. So we will maximize our minimax objective function for the discriminator while holding the generator fixed. Then we, and then we do the same thing for the generator. And so this, you should recognize this term for this generator objective as the right-hand side of that minimax objective. And that's about it. That's how you train GANs. And so yeah, then you just trade off between training the discriminator and training your generator. Yes. Oh, good observation. So yeah, this is saying that we're updating the discriminator for k steps, and then we're updating the generator only once. In practice, the GAN paper, I'm pretty sure they used k equals 1. So they would take 1 step on the discriminator and then 1 step on the generator. Yeah. But I mean, it is an important note to make because one of the main problems that we have with GANs is that the learning of the discriminator outpacing the learning of the generator. And so you really do want to balance those. Yeah, Chase? Yeah, so yeah, and yeah, totally. You could totally imagine an algorithm where you adjust the training speed of the generator or the discriminator based on which one is winning. Yeah, cool. To be honest, I personally have not worked a lot with GANs, and so I don't have a ton of practical experience to answer that question. So the answer is I don't know, but I bet if you looked it up, you could find the answer. Okay, so this is a sample architecture for a convolutional GAN. This is the DC GAN, deep convolutional GAN. So we see that it takes as input 100 by Z, a 100 dimensional Z vector, and then turns that into a 4 by 4 by 1024 tensor. Any ideas what operation we would use to go from a 100 dimensional Z vector to a 4 by 4 by 1024? Someone in the back? The question is, what kind of layer would we use to go from a 100-dimensional Z vector to a 4x4 by 1024 tensor? Yeah, Dane? Exactly, yeah, a transpose convolution. So yeah, a 2D transpose convolution can increase our spatial dimensions. And so that's what we will be using at each of these layers, basically an upsampling neural network. Okay, so this is kind of a cool visualization based on this DC GAN architecture. So what they did is they drew a Z vector, and then they drew a different Z vector. And then they simulated samples along the path between A and B. So what this would look like is, and in fact, to generate this entire grid, I believe what they did is they generated two Z vectors, and then in the top left is 1 times A plus 0 times B, and the bottom right is 0 times B plus 1 times A is in the top left and B is in the bottom right, and then we can interpolate between those Z vectors. So what that looks like is we have lambda times A plus 1 minus lambda times B, and then we gradually adjust lambda to turn vector A into vector B. And then and so that's what it looks like, is we're going across this image or up this image. And then we take those Z vectors, we call this interpolation between vector A and vector B, and we pass those Z vectors through our generator and generate images. And so the result is this interesting, we would call it like a manifold of images, where we can see that there's a continuous relationship between the Z vector that we choose and the images that we generate. So based on that understanding of, I guess, yeah, any questions on how we generated this image? Yeah, Michael? Yep, drawing about 2 vectors from the Z space. Correct. Yep, these are just 100-dimensional vectors. And then no, so these do not refer. So if you look closely, this is a grid of small generated images that are all supposed to look like numbers. So each of these is a generated image corresponding to a Z vector. Exactly, yeah. So they're linearly interpolating between the 2 vectors, which is the shortest path between them. So then we'll use that to get like 10 different Z vectors, and then we're going to use our generator to translate those Z vectors into numbers, or sorry, into images of numbers. Yeah, what do you notice about do you notice any patterns in this interpolation space of images? Yeah, Dane, what do you notice? Exactly, yeah. So Dane's observing that looks like 7s turn into 1s, which then kind of inflate back into zeros. Yeah. What else? Sam. You have a lot of zeros in multiple parts, but only about 10 2s. That is true. Yeah, so a couple of interesting things on that. I don't know that it's harder for this network to represent twos. It may just be a function of the place in Z space that we are. But I do think it's interesting that, yeah, we have zeros in multiple places. We have zeros that are similar to 5s, zeros that are similar to 8s, and zeros that are similar to 6s, which is kind of interesting. So yeah, this generator is kind of learning to place numbers that are visually similar to each other in similar places in Z space. So these are a couple more interpolation examples. Now this visualization is, we are taking now real images and interpolating or images of people and interpolating between them. Now, if you remember, we don't have a way of going from an image to a Z vector with our generator, right? We don't have any way of the backwards function. And so because of that, in this example, because we're starting with real life images, we need some way of mapping those images into a latent space to do interpolation. And so basically what this visualization is between the first column and the second column, we have found kind of the nearest neighbor in Z space to our true image, and then found the nearest neighbor in Z space to our other true image. And then once we have those closest matches, we interpolate between them in Z space. And yeah, you can see like one face kind of transform into another. It's pretty interesting. Any thoughts or comments on this in this visualization? Yeah, Brennan. Great question. So the question is, why does this mapping from image to Z space, why is that a bigger gap than any of these other gaps? And the answer is that in this case, it's a weakness of the algorithm that it wasn't able to find a neighbor in Z space that was close enough. So I know kind of an unsatisfying answer, but yeah, Chase. That's a great question. If you were to increase the dimension of your Z space, potentially, for sure. Or yeah, other things might be related. So it might be related to the size of your Z space or the representational capacity of your data set. Like, does our data set have people smoking cigarettes in it? I don't know, you know? Yeah. So this is an interesting comparison between interpolation in pixel space versus interpolation in Z space. So if we were to do the same method, but with the pixels of the images instead of with the Z vectors of the images, you end up with these kind of weird ghosty looking things that don't really look like true samples from the data distribution. Whereas if we interpolate in Z space, then you can see that we are starting to get intermediate images that look more like samples from our data set. And the deeper we go into, so you can also do interpolation at other steps of the generator. You can interpolate at layer 1, but you can also interpolate later and later. And the later you interpolate to the generation, the closer you get to the actual manifold of the training data. Some other fun things we can do with these Z vectors, we can do arithmetic like we did with word embeddings. So we're going to take the Z vector for a smiling woman, subtract the Z vector for a neutral woman, add the Z vector for a neutral man, and we end up with a smiling man. Same thing, take a man without glasses, a man with glasses, subtract a man without glasses, add a woman without glasses, and we get a woman with glasses. Yeah, then like, yeah, rotations of a face are linear in feature space. So yeah, basically the idea is that this feature space of Z's can be pretty useful for understanding relationships between images in we'll call it perceptual space instead of pixel space. A couple more examples of generated images: people, Pokemon, rooms, album covers, yoga poses. Yeah. Okay, so there's one more thing that I'd like to at least give a preview to you on today before we go. And this is text conditional GANs. Conditional GANs are super powerful. And I would say probably more so than just unconditional GANs. So an idea of where we're going, we want to be able to take a caption and produce an image that matches that caption. So there's this paper called Generative Adversarial Text-to-Image Synthesis, and this is its architecture. So first, we are going to take a z-vector sampled from a normal distribution. That should look familiar. We're also going to take a sentence embedding vector. Any ideas how we might turn a sentence into a vector? Hopefully you should have some ideas at this point in the class. Yeah, I heard word2vec. Anything else? You can just shout them out. LSTM. What? Yeah, other word embeddings. Yeah, transformers. Totally. So we get a sentence embedding. Concatenate that with our z-vector, and that becomes the input to our generator. Our discriminator then takes as input an image, a generated image or a real image, as well as a caption, the same embedding for that caption, and tries to discriminate whether that image is real and whether the image matches the caption. So this is the algorithm. So we're going to sample a mini batch of images with their matching text, as well as mismatching text for each of those images. Then we will encode the matching text descriptions, encode the mismatching text descriptions, sample a z-vector, pass the z-vector as well as the true descriptions through the generator, and then subsequently pass them through the discriminator to get a score for the real image right text pairs. Then we'll also do the same thing for real image wrong text pairs and for fake image correct text pairs. And we want to maximize the log maximize the log probability of the real image right text. We want to maximize like the classification of the real image right text. So we want the discriminator to predict 1 for the real image and right text, and 0 for the real image wrong text and fake image right text. Then we update our discriminator, and then our generator just wants to maximize the likelihood of wait, is that right? Oh yeah, the generator is trying to fool the discriminator by producing fake images for the right text. Or trying to get the discriminator to think that, sorry, let me think about that. I don't know about what this line says exactly, but our generator is trying to fool the discriminator into thinking that its generated images are real images with the right text. So I think this should maybe be SR instead of SF, but I'll get back to you on that. Then we update our generator. And that's our conditional GAN training algorithm. And don't worry, we will go more into detail on it next.